Hi, thank you. So I'm going to talk about enabling reconstruction of attacks on users using efficient browsing snapshots. This work was done, this is a joint work done with Jianan Liu, Bo Lee, Dr. Babak Rabarinia, Dr. Kyuhung Lee, and Dr. Roberto Perdici, who's also my PhD advisor. So let me get started. Let me start with the case study. Say there's a large corporate network with a lot of machines, and on an unlucky day, an employee named Bob falls prey to a new kind of social engineering attack. The result is that a few machines get infected, and some sensitive company data is leaked to the internet. So a forensic analyst is hired to investigate the incident, and they find the root of the infection and clean up all the infected machines. But this is not sufficient, right? Because tomorrow another employee might again be subject to the same kind of attack. The main vulnerability, which is the lack of user awareness about this incident, about this attack, still remains. So to plug this gap, what we need is to find out what exactly Bob saw on that malicious page on that fateful day and how he interacted with the page. If we know that, we'll be able to understand fully how the attack happened and then train users so as to prevent this attack from happening again in the future. To be more concrete, what we need is a tool that can record and reconstruct user-browser interactions as well as browser state. There are a few requirements that such a tool should meet. First of all, the browser state should be captured synchronously, meaning that it should be captured even before the processing of the user interaction begins. Otherwise, a malicious page can process the input and change the browser state. Next, because these kind of user attacks are unpredictable, we need a solution that is always on and efficient. So in order to ensure efficiency, we have set a time lag budget of about 150 milliseconds for our tool. Next, attackers shouldn't be able to easily detect the presence of a tool. And finally, it'll be nice to have a tool that will work on multiple operating systems, including mobile devices. So for building such a tool, we looked at some of the related research works and saw that none of them meet all the requirements. Either visual reconstruction is not possible, or the reconstruction is not deterministic, or the tool itself is too heavyweight to be used as an always-on portable tool. So we built ChromePic, which is an always-on, efficient, and portable forensic engine that is embedded within the Chromium web browser. It synchronously records user browser interactions as well as the browser state into rich forensic logs that we call Webshots. So what's a Webshot? A Webshot contains user browser interactions, which could be a mouse click, in which case we store the coordinates of the click, or it could be a key press, in which case we store the key code. Along with this, we store the timestamp. And to capture a visual state of the browser, we take a screenshot of the active tab. To get the structural state of the browser, we store what we call a DOM snapshot. It includes the DOM tree and embedded objects such as images and scripts for all the frames in the page. And to make ChromePic efficient, we only capture these web shots when there's a significant user-browser interaction. So we call them trigger events. Example trigger events are clicks on mouse, or when there's a tap with a touch device, or keyboard actions like return, space, tab. All these are trigger events. So how do we use ChromePic? Once ChromePic is deployed, we can lay all these captured web shots in sort of like a timeline, and we can go back to any time that we are interested in investigating. At that time, we can see exactly what the user saw when he was browsing, what all elements and scripts were in the page at that time, as well as what input the user gave to the page at that time. This will help us fully understand any kind of attacks that might have happened during that time. Next, let's get into design of ChromePic. For building ChromePic, we first tried to use the extension approach, but that was not efficient. So we decided to instrument the Chromium browser instead. Chromium browser has a multi-process architecture. There are multiple tab-specific processes called the renderer process, which take care of things like parsing of HTML and JavaScript execution. And for all the tabs, there's one process called the browser process, which does things like file input, output, and interacting with the users. So when there's a user input, the browser's UI thread receives it, and with the help of an IPC message, it relays it all the way to the renderer's render thread. The renderer's render thread is where all the input processing takes place. Now, to instrument Chromium, we wanted to use as much of the underlying pre-existing code as possible. In Chromium's code base, we found a function that can asynchronously take screenshots. But this runs on the browser's UI thread. And then there was another function that can asynchronously take create an MHTML dump of the page. This is basically the DOM snapshot that I defined. And this works in the renderer's render thread. But these two are asynchronous. We needed synchronous and efficient versions. So we kept this requirement in mind when we were designing ChromePic. This is how ChromePic works when there is a trigger input. The browser's UI thread receives it and relays the input immediately to the render thread, just like it does in the regular Chromium browser. But in ChromePic, in addition, it also makes a request, an asynchronous request to capture a screenshot. And then the UI thread waits for the request to be satisfied and then sends a custom notification to the render thread that the screenshot was taken. Meanwhile, the render thread requests and waits for DOM snapshot to be captured. After that, if needed, it waits for the screenshot notification. And only then the regular input processing happens. So by design, we're making sure that ChromePic captures Webshots in a synchronous manner. Next, we needed to ensure that both screenshots and DOM snapshots were taken efficiently. For screenshots, when we used the Chromium's code as is, we found that we had to wait a long time for a screenshot notification to return. Sometimes it took as long as 1 second. This was simply not efficient enough to be used. So we dived deeper into the code and saw that there was a point in the code where the pixels of the screenshot are safely being copied into a buffer. So if we send a notification at this point itself, we could save some time. How much time did we save? It turned out that this point is reached every time the browser tries to draw a frame. And browsers try to draw a frame every 16 milliseconds. So we were able to reduce the screenshot notification time to 16 milliseconds, which worked for us. Then moving on to DOM snapshots, the original Chromium code for taking an HTML dump of the page is pretty complex. As you can see, it does it on a frame-by-frame basis. So for every frame, a request is sent to the render thread to dump its MHTML. This means that a number of, for a single MHTML job, a number of tasks are scheduled on the render thread. But the render thread is like a very congested place in Chromium browser. So it is very likely that an unrelated task will be scheduled in between, and it will delay the process of dumping MHTML. So what we decided was to process all the frames in just one task. And also we piggyback this task onto the input processing task, which is anyway bound to be scheduled on the render thread. This way we made sure that they were not putting any additional scheduling delays. So this meant that what was previously taking seconds, we were able to finish most of the time in less than 150 milliseconds. So this concludes the design. Let's get into evaluation of ChromePic. We evaluated ChromePic by testing it on various UI attack pages. There was an in-the-wild social engineering attack page, a real-world phishing page, and a couple of clickjacking attacks from previous research. I'm going to talk about the social engineering attack here. The others are discussed in the paper. So we came across this attack when we were doing a user study with an Android tablet. The way the attack worked was when the user makes a web search query for a stream of a popular movie, one of the top resulting pages popped open a tab that contained a malicious ad. It was kind of like a fake AV scam, claiming that the tablet is infected and directing to an app on the App Store. So this is some of the data from the real web shots that were captured during the attack. So as you can see the screenshots from the user's screen, as well as the input that the user made at that time. There's a key press and a few taps. And from the DOM snapshot that was captured, we were also able to recover the text of an alert window, JavaScript alert window that popped up on the malicious page. We also got the URL of the app from the DOM snapshot. So this is how we can basically use ChromePic to analyze a real-world attack. Next, we wanted to do a user study to measure performance of ChromePic on real-world user behavior. So for this user study, we used an Ubuntu desktop, an Ubuntu laptop, and an Android tablet. And in total, there were about 22 distinct users who browsed for more than 16 hours. And they were visited about more than 200 unique domains. In total, in the study, there were about 6,000 web shots that were captured. So I'll present some of the performance results from this study. On the left, you can see times it took, time that we spent waiting for a screenshot notification when we used Chromium's code, the original code as is. So you can see the times listed for the 3 devices at both the 50 percentile and the 98 percentile. On the right, you can see how these times are greatly reduced when we use the optimization technique that we mentioned. Basically, most of the time, in less than 30 milliseconds, we got a notification that the screenshot has been captured. Moving on the right, you can see the overhead for capture of DOM snapshot. And we can see that comparatively, this is more than the times for screenshot capture. What this means is that when ChromePic is running, by the time the DOM snapshot is captured, most of the time, the screenshot notification would already arrive. So the total webshot overhead is basically the same as the DOM snapshot overhead. And how much is this? For laptop and desktop, it's about 100 milliseconds, which is less than our target rate of 150 milliseconds. For the Android tablet also, more than 89% of the cases, we have been able to capture a webshot in less than 150 milliseconds. To further put this into perspective, there's this CDF. The solid lines indicate the distribution of webshot overheads for the 3 devices. The broken lines indicate the time taken by the users in the user study to either press a key or click a button. So you can see that the solid lines are to the left of the broken lines mostly. What this basically means is that even before a user lifts his finger off of a mouse button, we can actually capture the webshot. So it is unlikely for the user to notice any lag. We also wanted to use the data from the user study to measure performance, measure storage requirements. We noticed that we need about 1 megabyte of disk space per minute of active browsing. So at this rate, like a 1,000-employee corporate network would require about 72 terabyte of disk space to store 1 year's logs, so which we think is kind of manageable. Finally, to mitigate privacy, we can use things like disabling ChromePic on HTTPS connections or whitelisting sensitive websites. We can also use the site-based encryption keys, separate site-based encryption keys to encrypt the logs from ChromePic. To conclude, ChromePic is a lightweight and portable forensic engine that's embedded within the Chromium web browser. We can efficiently record and reconstruct UI attacks that have a significant visual component. Thank you. We are going to release the source code very soon. We already have the binaries available for download for both the Linux and the Android platforms. I can take any questions.